It's actually a very interesting calculation. So we stress here that when you can compare the presence of electric fields in different parts of the universe, on our scale you might have something of the order of tens to hundreds to kilovolts per meter. So in order, for example, to get air to conduct electricity, you have to have about 3 megavolts per centimetre. If you go down to the atomic scale and you calculate with the charge on the nucleus of an atom and the distance that the electric fields are being applied over, and you scale them up to our level, the electric fields are literally gigantic. They're of the order of 10 to the 10 volts per metre and even more. So that you wouldn't be able to, for example, if you had 2 charged plates and they were operating with the same potentials that you'd have at the atom, you wouldn't be able to pull them apart with any mechanism that we know about now. And it's largely these atomic electric fields that stop you disappearing through your chairs, through the floor, through to the other side of the earth and oscillating backwards and forwards. It's the electrostatic forces that actually make it possible for you to interact with matter, not to pass through or do bizarre things like that. So what we have in now dealing with this polarization response is we can talk about the susceptibility, because different materials are going to respond in different ways depending on whether they have a weak resistance to the electric field or they're strong. We talk about their susceptibility to the impressed electric field. And that introduces us to a new symbol that you often come across when you're reading this literature. And we can say here that the polarization, which is a vector itself, as a function of another vector, the electric field, is going to be proportional to the magnitude of that electric field. So it's a simple proportionality. It's a linear response. Although we won't discuss it for this course, you can nowadays put a laser beam signal down an optic fibre. In that case, we have to consider, if you do a Taylor's power series expansion, I'll look at that briefly at the end, you have to add higher power order terms of the electric field, E squared, E cubed, etc. But we're largely going to terminate our discussion for this course simply at the first power of the electric field. But be aware that certainly in crystal optics, you have to invoke at least the second power of the electric field in order to understand polarization response. The constant of proportionality, we'll just take this further. This is a Greek letter, P, C-H-I, Greek letter. That's conventionally the symbol that they use for the susceptance, the electric susceptance of a material. So because effectively you've got an equation y equals mx plus b, there's no intercept given at this equation, at this point. You've just essentially got the equation of a line, so that the susceptibility is the gradient in that linear relationship. So we can now reformulate D, the displacement vector, to be equal to the electric field plus, which we had as 4 pi. And we're simply just going to substitute in. So we bring in this extra term now of the susceptance.
for susceptibility. And this is about susceptibility. So was that.
So, obviously we can write the displacement vector to be equal to, I'll explain this very shortly, but essentially this square matrix operator, again we use this letter from the Greek alphabet. Now sometimes you will find that in the literature they'll use epsilon for permittivity. The reason it's not used in this course is because it's confused in other parts of electromagnetism and antenna theory, where this is reserved for the radiant efficiency of an antenna system. So this is the emissivity of a material. So instead we use kappa for the relative permittivity of material. And you'll find that it's a pretty even 50-50 split between textbooks around the world as to which ones they use. But certainly in this school with antenna theory, for those of you who go on to do, if you do a master's course and it's in antennas, you will find that we use emissivity and use that symbol. But be aware in your online lecture notes that this other one is otherwise used for historical reasons from previous lecturers in the course. So you've got a choice. If you understand what's going on, by all means stick with epsilon in terms of other books, but be aware that other people more commonly use kappa, the Greek letter kappa. And K is what they call the dielectric constant. If you expand that expression, so using full matrix notation, what you end up having is a displacement vector with components. So you've got an x, y, and z component of the displacement vector, and it's going to be proportional to the impressed electric field. So you're going to have the x and y and z component of an electric field. So you can imagine some in your coordinate system, x, y, z, you've got some lump of material, whatever it is. The electric field can be applied in some fashion across the system, but depending on what your operator is going to be, the reaction field inside the material could be something of this form. This is just a little scribbled cartoon. You could do a probably better one in your notes. There's the applied field, and D would be the reaction field in the material. So here's our, you've got KXX, KXY, KXZ, KYY, KYZ, KZ, X, ZY, KZ. This is you can either think of this in from linear algebra that you would have done as an operator, but in crystal optics and in the general study of optics, they call this a second order tensor. So any square matrix is a particular example of a second order tensor. If you extend this matrix into 3 dimensions, So you can imagine you have kxx, so you've got 3 x's, then an xxy, etc. So you've got a cube, and in each of the, you've got here 9 addresses, but if you've got a cube, 3 by 3 by 3, you can imagine now that you've got a 3-dimensional response of the material to the electric field in the most general case. When you plot this, this is when you multiply the E field by this operator matrix, it generates for you the reaction field D within the material. So this is the general displacement vector. I don't think in your notes it opens it out in this to this degree, but nonetheless, in reality, this is what we're talking about. So you need to be aware of that.
Excuse me. Then the K should be vector as well. The K kappa.
It's in the braces. It's implicit.
So
As soon as you put the brackets around it, it's a matrix.
So what does it show is a vector?
This isn't a vector. It's a matrix. It's an operator. K is not a vector.
Then why is changing the direction of E field? I mean, if you take the case of isotropic...
No, I'm just saying that if you had an E field impressed in a particular direction, this would be arbitrarily the reaction field. So the dipole response might be of that character, or it could be far more complicated than that. But the dielectric constant, in this particular case, is not a vector. It's a square operator.
So what you're assuming, is this the material non-isotropic or the isotropic?
I'll get to that. Because if you're aware of what isotropy means, it doesn't matter in what direction you look within the material, you don't recognize any change. So it's directionally independent. In that case then, if you had an isotropic material, you would actually have entries like that. That meant that you would have a reaction that did not have any change. It was left the material was left unchanged.
So that's a scaled version of your E field.
So this would describe a material that was not susceptible to the application of the electric field because it was left unchanged. If you have off-diagonal entries, for example, that are non-zero, that is where you get optical activity, such as birefringence, for example, or pyroelectricity, or things of that nature. I'll have a short note at the end to deal with that, but primarily we're concerned with these kinds of materials.
So this is just a scaled version of your E field, if you find that.
Yeah, essentially, yes.
So when you move to anisotropic in the matrix form, that's why there's a confusion like that. I thought it's a vector because it's changing the electric field direction.
Yeah, essentially, because if you, as you're saying, if you have main diagonal entries, and they're either one or multiples of one, either to amplify or decrease these terms, you're right, you've got a scaled response of the electric field in terms of the reaction. Sorry?
Then this one would be the vector response of it.
That's right, there's the vector response, there are some components. The X, Y, Z component of the reaction field. Everyone's here now. So, just to make a note here. So just to epsilon subscript R, R is for relative. And it's relative, so there's the, it's relative to the permittivity, epsilon subscript R. And the reason why I'm keeping epsilon here and not using kappa is because I have a subscript R, which makes explicit that we are dealing with the idea of permittivity and not something else like emissivity, as I talked about earlier. So the relative permittivity is relative to the permittivity of free space. the vacuum response, in other words. i.e. permittivity of so-called free, as in free of material, space.